Good afternoon, everybody. Welcome to Taco's Comfort Solution University's Chill Beam presentation, another great Taco Tuesday webinar presented by the commercial folks at Taco. Rich, I just want to check, are you hearing me right now?
Yes, I can hear you and I can see the screen. Looks good.
Okay, good. All right, so hopefully some of you have been on this before. My name is Brett Zerba. I'm an applications engineer with Taco. Have been with the company almost 25 years. Holy moly, but I love Taco. It's a great company. We are headquartered in Cranston, Rhode Island, worldwide company now. Places in Canada, places in across the country. We have another facility in Nashville, Tennessee. We have a facility in Italy, a facility in Vietnam. It's pretty, and one more in Sweden. Norway. Where's the? Oh yeah. But anyways, we have them all over the country. So today's presentation is on chilled beams by my good friend and co-worker Rich Medairos. I'll turn it over to him shortly. Before we get too far into today's presentation, and we want to make sure Rich and I can hear each other, but we want to make sure you can hear us and see us. So if you can click on that little wave button and wave the sign there, so you can wave us. Oh, good. I see a lot of hand waving going on. So thank you very much. So Frank, thank you, Frank. That was nice of you. Anyways, that's good. So also a couple other housekeeping things. There is a chat area. So feel free to type in there, but there's also the question area. And that's where, if you want to ask questions, just, my good friend Paulie Silvestri out of Pennsylvania is already asking some questions. Of course. Thanks, Paulie. He's with our great rep, BJ Taroni, down there in New Jersey and Pennsylvania area. So feel free to type your questions, and Rich and I will make sure we answer as many as we can during today's broadcast. If we don't get to them, as some of you know, we will answer them after the fact and get them back out to you as time permits the next couple of days. About 24 hours from today, you will receive an email with a link to the video of this. We are taping it, as well as a link to so you can download your PDH certificate. So be ready and be prepared for that. Other than that, I think I got all the basic stuff out of the way, and I'm getting ready to turn it over to Rich. Let's see, anything else? No handouts today, and attendees, we're doing well. And questions, type your questions in as we go. Rich, other than that, I think you're ready. Take it away, my friend.
Thanks, Brett, for that great introduction. Welcome, everyone. This is Rich Medairos. I'm actually broadcasting today from Massachusetts. We're having a mix of thunderstorms, light rain, and sunshine. So hopefully we'll get through this broadcast without any major electrical disruptions. So just a quick introduction about myself. I'm a mechanical engineer. I've been with Taco just under 8 years, and I only have 20 years left to go. So I'm working on my 10-year pin, and then only 20 years to go after that. So I am a PE, and I did spend a portion of my career on the consulting side of the fence. So I've been designing HVAC systems for a number of years right now. So today's presentation is about chill beams, and I call it the COVID-19 buster. And when you get through with as we get through, go through the presentation, you'll see why I call it the COVID-19 buster. So hopefully my computer is working and my slides should advance. Let's see. It does that? Yes. Okay. So here's the items we're going to be talking about: cooling load profile, water versus air efficiency, types of chill beams, primary air, which is the main focus for the COVID-19 buster, advantages of chill beams versus variable air volume, and sample project photos, and summary and questions at the end. All right, so let's get right into it. the first thing I like to talk about is the cooling load profile. And by that, I mean, what is going on with your cooling load and what are the different types of heat that you're trying to get rid of. So cooling load falls into two major categories. We either have what is known as sensible heat, and the simple definition is heat which is measured by a thermometer, sometimes referred to as a dry bulb thermometer, and no moisture is added to the space. The other category in our cooling load profile is latent heat. And latent heat is heat which is measured by a humidistat. And that's where moisture is added to the space or taken away from the space. So when we talk about latent heat adding to a space, we're adding moisture to that space. So let's look at some examples of each of these categories of heat. Here we have some light fixtures in the ceiling, and they add sensible heat to the space. I have a computer sitting on a table over here, and that adds sensible heat to the space. Now we have a plant, and let's assume that that plant is a live plant, and periodically someone waters that plant and the water evaporates, and since we're adding moisture to the space, that plant is adding latent heat to the space. And we have a printer over here that also adds sensible heat. Now there's a trend building here. You'll see that the majority of items that I've called out add sensible heat, and then we have a minority grouping that add latent heat. As it turns out, if we do a complete inventory, including the people in the space and the outside air, turns out about 80% of the heat that's added to the space is sensible heat, and about 20% is latent heat. So as the old expression goes, we want to reach for the low-hanging fruit. And it seems logical that if the overwhelming majority of heat that's being added to the space is sensible heat, perhaps we could remove that heat independent from removing the latent heat. And if we could do that, we would get rid of the overwhelming majority of heat that's inside of a space. So let's focus our attention initially on the sensible heat. Okay. So here we have two means or mechanisms of getting rid of sensible heat. One is water and the other is air. And let's look at how efficient each one of those different methodologies are. So if you'll notice, I'll get my little pen drawing tool here. And let me choose a color for today's color. Today I like red. So we're going to have a red pen today. Here's my pen. So if we have some cooling load and we have 1 ton of cooling, we would have 12,000 BTUs per hour of sensible cooling. Now remember, I'm only focused initially on sensible heat. So if I have 1 ton of sensible cooling, that's 12,000 BTUs per hour. If I had a supply air temperature differential of about 20 degrees Fahrenheit, I would need roughly 555 CFM to displace that 12,000 BTUs per hour. If I was doing that same amount of sensible heat removal with just water, I would need only 2.4 gallons per minute of water. So if I was transporting air into a space in order to get rid of my 1 ton of cooling load, I would need, for a reasonable velocity, a duct that was approximately 10 inches by 12 inches. And that would deliver 555 CFM of air. If I was moving water into the space, I could do that with a 3/4 inch diameter pipe. And I could move 2.4 gallons per minute. Any questions about what I've done so far? Anybody have any concerns about my 555 CFM?
Nothing's typed in the question area, Rich. Usually people say that that's a little high.
Really? Well, if I take 12,000 BTUs per hour and I divide that by the constant 1.08 and divide it by a 20-degree delta T, it comes out to 555. Now, if I multiply that by times 0.72, it comes out to exactly 400 CFM. So a lot of people might think that 400 CFM per ton is the right number, but when we're talking about 400 CFM per ton in a conventional system, we're saying that that 400 CFM has the ability to remove 72% sensible heat and 28% latent heat. But in our case, we're just getting rid of sensible heat initially. We will talk about latent heat later. Okay, let's continue along here. Where's my erasing tool? Erase all. Oh, there, I found it. Son of a gun. Okay, so let's go off and look at, now let's look at how much horsepower it takes to move air versus water. So given 100 tons of sensible load, I'm going to start off here, 100 tons. Remember, I said 555 for 1 ton. Well, 100 times 555 would be 55,500 CFM. If I move that air against a resistance, I just realized I spelled the word resistance wrong. Look at that, Brett. Sorry about that. And if I had 7 inches of water column, 75% fan efficiency, it would take me 80 horsepower to move that air. If I was doing that with water, remember we had 2.4 GPM per ton. Well, for 100 tons, we would have 240 GPM. And at a resistance of 100 feet of water column, same efficiency for the pump as it is for the fan, 75%, that would only require 8 horsepower. So it turns out we need 10 times as much horsepower to move air versus water for the same amount of sensible heat removal. By the way, this is the fundamental reason why chill beams are so much more energy efficient than conventional all-air systems. So this is an important slide. It really does drive home the point that it takes significant amount of horsepower to move air for the same sensible load as it does water. Any questions about that, Brett? Anybody have any concerns?
There is a question. Hello, even before we go forward, why does anyone use air then? It's 10 times more expensive.
It is in terms of horsepower, absolutely correct. But in the United States especially, well, let me just say North America, which includes the US and Canada. I mean, all air systems were basically the fundamental HVAC system. But chill beam systems are extremely popular in Europe. And Europe has moved ahead in almost all new construction. They're using some form of chill beam technology. And they're taking advantage of the huge horsepower savings. So if any of the folks out in the listening audience may have had an opportunity to visit our headquarters building in Cranston, Rhode Island, we have a chill beam system. So we are taking advantage of this huge horsepower savings. And chill beam systems are becoming more and more popular. They're not the most popular system, but they are becoming more and more popular. The major competitor against chill beam systems are all air variable air volume systems. And so we're seeing more and more interest in chill beam systems because of the horsepower savings. Brett, any other questions out there?
Just a comment. The fear is condensation.
Ah, excellent point. We will touch base on that in a couple of minutes. Okay, so I'm going to assume there's no other questions about this sheet, so I'm going to erase these little circles. And let's go off to the next sheet. So there are three types of chill beams. There are other variations, but the three major types of chill beams include chilled ceilings or radiant effect ceilings, passive chill beams, and active chill beams. So let's look at each one a little bit closer. The first category is called a chilled ceiling, which is called the radiant effect. And the chilled ceiling is nothing more than an extruded aluminum panel. I'll get my little pen over here so I can point. So here we have an extruded aluminum panel. It's on a hinge, so it's folded down from the ceiling. And on the back side, there is copper tubing attached. And that copper tubing runs back and forth in a serpentine arrangement. And we're supplying chilled water to that panel. But the space temperature is approximately 72 degrees Fahrenheit, and we're trying to maintain approximately 45% relative humidity. That means our dew point temperature is approximately 50 degrees Fahrenheit. So when we circulate chilled water through this radiant panel, we want to circulate that water above the dew point temperature so it does not create any condensation. So if you'll notice over here, the supply water temperature on the left-hand side is somewhere around 59 to 62 degrees. Now, depending on your comfort level, some people are willing to go down as low as 52 degrees Fahrenheit. That's only 2 degrees above our dew point temperature. Most people are designing systems today to be in the range of 55 to 60 degrees Fahrenheit. And we're going to look at a couple of options in a few minutes. So that's all there is to a chilled ceiling. They became popular actually in the mid to late 70s, actually, when people started adding computers to desktops, and there was a tremendous increase of sensible load. And so rather than redoing the entire system in some of these buildings, they just simply put in radiant ceiling panels to transfer that radiant heat. Now, again, we are circulating the chilled water above the dew point temperature. In this case, the dew point temperature is approximately 50 degrees. So we're somewhere between 55 and 60 degrees. We're definitely above the dew point, so we're not creating any condensate, and we're not removing any latent heat from the space. So this is only doing sensible heat removal. Okay, the next one, let me erase some of this stuff here, is called a passive chill beam. Now, a passive chill beam is nothing more than a cooling coil inside of a box. And again, exactly the same room conditions. I have a dew point temperature of 50 degrees Fahrenheit. If I circulate chilled water above the dew point temperature, then this device will remove sensible heat. So let's take a look at it in an actual ceiling arrangement. So here we have a perforated ceiling. Let me get my pen out here. Here we have a perforated ceiling. I didn't grab my pen, sorry. We have a perforated ceiling indicated here by this dotted line. We have the actual coil. The gray area represents the fins. The white areas represents the copper tubing that's inside the coil. And that's just inside of a box. It's just a conventional coil. There's nothing special about it. And we are circulating chilled water. Again, we're circulating that chilled water above the dew point temperature. And in our case, the dew point temperature is approximately 50 degrees Fahrenheit. So we're circulating chilled water somewhere between 52 and 60 degrees Fahrenheit. And when we do that, the coils will cool off and the warm air will hit the coil and drop through the ceiling. So I do have a slide here with some animation on it, and hopefully that will work. I'll go to the next slide. Let me erase some of that notes. And here is a animation that shows the warm air hits the coil, cools off, and the change in specific gravity causes the air just simply to drop in the space. Now, one of the advantages of a passive chill beam versus a radiant panel is that the passive chill beam has more surface area, and therefore it has more capacity. Let me go back to the radiant panel for a moment. The radiant panel is actually the same physical device as a radiant heating panel, which means that I could either circulate chilled water or hot water through this radiant panel. If I want circulated hot water, I could do heating in the winter, and if I circulated chilled water, again, above the dew point temperature, I could do sensible cooling in the summer. However, the passive chill beam can only do cooling, because if I started circulating hot water, all I'd wind up doing is heating the space above the ceiling. So I just make the ceiling cavity warm in the wintertime, and I wouldn't drive any heat down into the space. So you've seen two examples of components in the chill beam category that can remove sensible heat independent of removing any latent heat. So these two devices do not remove any latent heat. All right, and here's what they might look like if you had multiple units in a room. Any questions about either the radiant panel or the passive chill beam? Anything out there, Brett?
There's a comment about sometimes the dew point can be higher than 50 degrees F. What is the solution for it? So I'm sure you'll cover that when you get into some of the distribution, correct?
Yes, we're definitely going to be talking about how to control dew point temperature. So that's a great question.
Yeah, and then there was a kind of a question pertaining to, you know, chill beams are part of a system. I think we all realize that, right? They're not standalone items. They need to be connected to something. And part of that system, when you talk about energy savings, massive energy savings, is someone saying that might be a bit unfair. You have to look at total energy used, including creating the chilled water somewhere.
That's an important point, yes. And it turns out the total refrigeration requirement is the same in this building than it would be in a in a chill beam system as it would a conventional, because ultimately the amount of heat that you're taking out of the building and moving it into the atmosphere is the same. But the mechanism by which you do it is different. And transporting the medium, air versus water, is much more energy efficient in terms of the transportation side, not in terms of the refrigeration. The refrigeration cost is the same. Hopefully that, and we'll get into a little bit more detail in a minute. Yep. Anything else, Brett?
No, I think that's good. We'll cover some other ones in a bit.
Okay. So let's go to the next slide and look at the actual workhorse of the industry today. Is called the active chill beam. Now, the active chill beam combines a couple of technologies into one technology. This particular photograph that I have here shows an active chill beam with a primary air connection. That's right here. I'm actually going to connect a duct to that. In this case, this is a 4-pipe unit, which means I have chilled water supply and return. Let's say these two guys are chilled water supply and return. And then I have hot water supply and return. We actually, this is the type that we have in our building in Cranston, Rhode Island. Now they come either 2-pipe or 4-pipe. If they're 4-pipe, generally speaking, the coil, which we'll show you a little bit more detail about, is 2/3 chilled water coil and 1/3 hot water coil. If it's a 2-pipe chill beam, then the entire coil is either heating or cooling, but there is a changeover. So the piping system has to deliver either chilled water or hot water. And again, in this context, the chilled water is always above the dew point temperature. So let's look at this chill beam in cross section and see how it actually operates. Erase some of those lines, go to the next slide here. So here is a chill beam in cross section. And if you'll notice, I have primary air on the left side here. Get my pen again. primary air on the left side, that's coming from a dedicated outside air system, which we'll talk about in a moment. That supply air, depending on your design philosophy, could be anywhere between 55 and 65 degrees Fahrenheit. Now, the way this works, it actually has two chambers. And I'm just kind of make a squiggly mark over here. This is the upper chamber, and this is the lower chamber. What happens is that air from the primary system that's ducted, remember that's a ductwork connection, enters the upper chamber and then passes through these nozzles right here. There's one set of nozzles on that side of the chill beam and another set of nozzles on that side of the chill beam. And when that air passes through these nozzles, the air increases in velocity. And when that happens, it creates a lower pressure. I'm going to put a couple of minus signs over here in this chamber, allowing air to be induced across the coil from the room. So the air is induced across the coil like that. Now the coil itself is just a conventional coil. It just has fins and tubes just like any other cooling coil. If we're in the cooling mode, we are going to supply chilled water to the cooling coil at approximately 52 degrees Fahrenheit in this example. Remember, we could be anywhere from 55 to 65. Here we chose a little bit less than 55. I'm sorry, that's the primary air. The water temperature, 52. And again, that's because the dew point temperature is 50 degrees Fahrenheit. We could make the supply water temperature higher than that. I typically like to make about 5 degrees higher than the dew point temperature. But in this example, it's 52 degrees, and that's 2 degrees above the dew point. That means that this coil is, all the work that this coil is doing is removing sensible heat. It's not removing any latent heat whatsoever. And if you'll notice, the induced air is approximately 300 CFM. That's what she's shown down here. So that room air is going up like this, and it's 300 CFM. And that's combining with the outside air from the energy recovery unit, or the dedicated outside air unit, or DOAS unit, which we'll talk about. So we got 100 plus 300, that's a total of 400 that's entering the space, 200 on each side. 200 coming out on this side here, and 200 coming out on this side over here. So the total air that's being moved in the space is 400 CFM. However, the primary air is only 100 CFM. This is the second category of energy savings. If this was an all-air variable air volume system, we would perhaps be moving 100% of that air, or 400 CFM, from the variable air volume box into the space in order to meet the space capacity. So in this case, we're using 1/4 of the total air. In some chill beam designs, people are designing systems at 1/5. So right now, this is the induction ratio here is 4:1. That's 400 total divided by 100 primary air. So that's a 4:1 induction ratio. Some people are designing to an induction ratio of 5:1. So they're producing, they're inducing rather, a total of 400 CFM with a primary air of 100. So the total is 500. So that's a 5:1 induction ratio. Okay, so let's put this guy also into animation, and let's see what it looks like. And I'm going to actually talk you through it as the animation goes. So the primary air enters the upper chamber, passes through these nozzles, increases in velocity, causes a localized low pressure that induces room air across and comes out both sides of the chill beam. So we've gone through several items here that affect the space and impact the energy consumption. Now, one of the most important concepts with a chill beam system is that this primary air eventually gets exhausted from the space and goes outside, is not recirculated. So The recirculation air is the 300 CFM, but that's within the space. It's not being recirculated to some other space, which is the first COVID-19 buster characteristics of a chilled beam system. Let me repeat that. The outside air, or primary air from the energy recovery unit, is 100% outside air. And so the exhaust air that leaves this space goes into our energy recovery unit and does not get recirculated to other spaces. The recirculation is done within the space itself. You can actually get chill beams with HEPA filters. This particular one does not show a HEPA filter, so you can get it with a HEPA filter. And I believe that a variation of this type of chilled beam is now being used in patient rooms with HEPA filters. So what does this look like with multiple units operating? Looks a little bit like this. And we got the warm air being induced across the coil. The coil is doing all the sensible, and the primary air is now doing the latent capacity. So let's go back to our little slide over here. This primary air has to have a low enough dew point temperature so that it has enough capacity to remove the latent load from the space. So the latent load essentially comes from, if you remember from our original diagram, it comes from the people that are in the space, and it also comes from the air that infiltrates from outside the space. It could also come from plants that are being watered, or if there are animals in the space, and so on. So the latent load is removed by the primary air, because the primary air has to have the conditions capable of removing the latent heat. So where does that primary air originate from? Well, let's take a look. Let me just skip over this little guy here. So here is a diagram of a dedicated outside air system, also known as a DOAS, D-O-A-S, dedicated outside air system. And this first section up here is one strategy that can be used. There are multiple strategies that are available today, but we wanted to show you one possible strategy. So in this supply air section here, we have a HEPA filter, so we're bringing in 100% outside air. That outside air temperature is typically, well, I shouldn't use the word typically. In the Northeast, we are using roughly 95 degrees dry bulb and 78 degrees wet bulb for our outside air conditions. That air is initially filtered through a HEPA filter system, and usually there is multiple filters in order to get the HEPA filter characteristics. It's now then passes through an energy recovery coil. And in this case, we're using hydronic coils, not an enthalpy wheel. And the reason we're doing that in this arrangement is because, again, this is a COVID-19 buster unit. So we are not taking any air that's being exhausted from the building and mixing it with any of the outside or fresh air. And since this is a runaround coil, let me just get my little pen over here. So we talked about the HEPA filter. That's this guy here, pointing to this guy. There's the HEPA filter. The runaround coil or runaround loop is actually a hydronic system, and it's taking and recirculating the water so the air does not get contaminated. So we can take exhaust air from the building, we'll get to that in a minute, and we can use that to cool off the outside air.
Your appointment is at 10 o'clock.
So we have 100% outside air. It passes through the HEPA filter, then the energy recovery coil. And if you're in the Northeast like we are, you may have a heating coil, you may not. And then we go into the cooling coil. The cooling coil in this particular case, let's say, is a chilled water cooling coil. And the chilled water temperature is somewhere around 40 degrees Fahrenheit. Now, in our building in Cranston, that is our design criteria, is 40 degrees Fahrenheit. That's for the chilled water coil right there. With that kind of low temperature, you can get an off-coil temperature of around 43 degrees Fahrenheit. Then we reheat that air back up to perhaps 65, which we've shown here. So that means that this has a supply air temperature of 65 degrees Fahrenheit, but it has a dew point temperature of 43 degrees Fahrenheit, which means that it is dry enough to have latent capacity. And again, latent capacity refers to the fact that we have a latent load in the space, and the latent load is the smaller percentage. In our example, it's about 20%. Now, the air that's being supplied to the chill beam, that's the primary air, that's the supply air here, that is connected to the chill beam. And then ultimately, we're exhausting that air, and when we exhaust that air from the space, it's approximately 74 degrees Fahrenheit. Now we have the heat recovery coil or energy recovery coil right here, excuse me. And in this case, we have 74 degrees. The outside air temperature is coming in at 95. So the difference between these two is approximately 21 degrees Fahrenheit. 21 degrees Fahrenheit. Sorry about that symbol there. If this coil arrangement was 80% effective, then that means that we would recover 80% of that temperature. So I'm going to take 21 times 0.8 and say that's 16.8 degrees. That means I can reduce that outside air temperature by 16.8. So that means my temperature here on this side of the coil is now going to be around 78 degrees Fahrenheit, dry bulb. So now in the summertime, the heating coil is off, passes through the heating coil, then hits the cooling coil. The cooling coil has enough capacity to reduce the supply air temperature down to 43 degrees, which is nearly 100% relative humidity on the discharge side of the coil over here. Then we reheat that air back up again. Now, there are a variety of methods to use for reheating that air. The method that we use, by the way, in Cranston is that we have a water-cooled chiller. So we're using water, diverting water from the cooling tower. That water temperature is around 95 degrees Fahrenheit. So it exits the chiller, condenser water, at 95 degrees Fahrenheit. And you can see we have enough capacity. We have enough temperature, rather, 95. And we're looking to reheat that air back up to 65. So that's a 30-degree approach temperature. So that allows us to essentially get free reheat off the waste heat coming off of the chiller. That's why I said this is one methodology that you can use for providing the supply air that you need at the right dry bulb temperature and the right dew point temperature. Any questions about our dedicated outside air system and what we've done?
Rich, we do have a few questions here. The first one is about the beams, the terminal unit. Okay, you talked about 3 different types. What kind of noise data is there? Some folks are a little worried about these being a little loud. You know, I don't think there's much on the radiant panels from a noise thing. But how about an active chill beam? What do you have for that?
Yeah, so when you go through the process of selecting an active chill beam, now we, TACO, do not manufacture chill beams. So the chill beam manufacturers out there provide software for selection. And one of the criteria that you're going to determine is your NC value, because these devices can be extremely quiet. When we selected the ones for our facility in Rhode Island, we wanted to have an NC value of less than 20. So the active chill beam, the amount of noise generated by the air that passes through the chill beam is an NC value of less than 20. So you can get them very, very quiet. But there are trade-offs, which is why when you go through the selection process, you have to define what you're looking for. Because the quieter you make the chill beam, the physically larger the chill beam is going to be in order to get the capacity that you're looking for. And I do have a photograph of our classroom, and I'll tell you a little bit about that. So yes, they can be very quiet as long as they're selected properly. Any other questions?
Yeah, a couple other ones. What would you suggest? You know, this is a great question as well about somebody opening up on a window. What's your thoughts on operable windows or not operable windows or whatever?
Yeah, that's a great question. You know, when it comes to designing chill beam systems, you have to work very closely with the architectural team, and you have to decide what kind of envelope that you're going to have in your building. So we try to push the concept of having non-operable windows. So that's your first line of defense. If you have to have operable windows, there's a variety of techniques that people can use. The simplest thing is they put a switch on the window, a dry contact. As soon as someone opens up the window, it sends a signal to the building automation system, and it tells the chill beam to shut down. Now, you know, that's one method. Another method is by carefully monitoring the space dew point temperature, and if you get an increase in dew point, rapid increase in dew point temperature, the building automation assumes that somebody has opened a window, in which case, again, it shuts the circulating chilled water down. So there's a variety of techniques. The first line of defense is to try and work with the design team and stay away from operable windows. Okay, any other questions?
One last question before you continue here. How does the heat exchange take place inside the energy recovery coil?
Okay, so these are just conventional coils. They're just fins and tubes, and we have a circulating pump here, this little guy right here. And the reason we call it a runaround loop is because the water is being circulated. It goes through this coil here, comes back out, up into the other coil, and you're just circulating fluid back and forth. So if your temperature, again, is 74 degrees exhaust air, and let's say that, again, that you're relatively effective, your effectiveness is 80%, then that means that you can get an off-coil temperature of around 78 degrees. I think it was around 78.5. What did I just calculate that out? It's around 78. We'll call it 78 right here. It's a little bit higher than that, around 78 degrees. So you're relying on two coils and the circulating water between the two coils. Now, most people, if these units, one of the advantages to this technology, by the way, is that the exhaust unit does not have to be connected physically to the supply unit. And so the advantage to that is that you could have all of your supply air coming in on one side of the building and all of the exhaust air going out another side of the building to reduce any possibility of cross-contamination of air. So that's all there is to the runaround loop. It's just a fluid, and a lot of people will use a water glycol solution, especially if these units are located on the roof of a building. That prevents the circulating runaround loop water from freezing. Any other questions, Brett?
No, well, let's move on for a little bit first.
Okay.
We might cover some of them.
All right, so let's erase all of these little lines here and go to the next slide. So here's a photograph of our main training classroom in Cranston, Rhode Island. And I'll grab a pen again. And here's the active chill beam. It's the same one that I showed you actually in that photograph before. And the supply air comes out of both sides, out of this slot here and this slot here. Now we have 9 active chill beams in the ceiling of this classroom. And if anybody visited the classroom, they realized just how quiet the system is. We actually shut off the projectors when we're doing a presentation. That's the ceiling mounted projectors, and we shut them off. It takes about 5 seconds or 10 seconds rather for them to cool off and shut off. And then when they do, the space is virtually silent because the system was designed, again, for an NC value of less than 20. We also have in that classroom, we have the radiant panels. That's this guy back here. And what you can't see very well, but there's a perforated ceiling right in the back of the classroom here, and that's where our passive chill beams are located. So we have 4 passive, 2 radiant panels, and 9 active chill beams. Now, we sized the active chill beams to handle 100% of the load. We can do sensible cooling with the radiant panel and the passive chill beam, and we do that as a demonstration. They're really not needed for capacity purposes, but we can run them. Okay, so that gives you an idea of how a typical classroom or office space could potentially be laid out. I'll erase this stuff here. Go to the next slide. So what are some of the advantages over a variable air volume system? Well, we said that the primary air is is less in a chill beam system than it is in an all air variable air volume system. So you wind up with smaller air handling units. Usually the air handling units are anywhere from 1/4 to 1/5 the size. So if you had a building that was, say, 500,000 square feet and in a conventional variable air volume system, you might be running at 0.8 CFM per square foot, which means you'd be running at around 400,000 CFM. In a chill beam system, you'd have anywhere from 1/4 to 1/5. We'll be conservative and say 1/4, which means that instead of having 400,000 CFM circulating in your building, you now only have 100,000. So your air handling units are obviously smaller. Your ductwork is smaller. You have less noise. There are no moving parts in a chill beam. There are no dampers, there are no motors, there are no fans, there are no moving parts. So the only noise that's generated by the chill beam is the air flowing across the nozzles to create the induction effect and the water that's flowing through the coils. And if you design the system so that you're circulating water less than 5 feet per second, which is a reasonable velocity for a hydronic system, for all practical purposes, you are in control of selecting the noise being generated by the chill beam in your selection process. And as I said earlier, I selected them to be at an NC of less than 20. So they have less noise. Lower maintenance because the terminal device does not have any moving parts. Again, there are no dampers, there are no fans, there are no valves, there's nothing associated with the chill beam. And what may not be obvious is that there is lower electrical infrastructure cost. What I mean by that is that keep in mind that if you had a 400,000 CFM airflow system, you would use about 1/10 the horsepower in a chill beam system as compared to a variable air volume system. And so that would impact your infrastructure. So, and I'm just making up a number just for example purposes. So perhaps you had in your all air system, you had a 5,000 amp service. Maybe you could go down to a 4,000 amp service. So that would reduce your electrical infrastructure cost because of the less horsepower in the primary air, and obviously lower operating costs. Okay. It's not advancing. Oh, there it goes. Now, the folks that helped us out in Cranston gave us this little slide. They were the folks that provided the chill beams were from Didanko, and they gave us this nice little slide, and they're predicting that you could save as much as 10 to 14 inches per floor in a 5-story building. I'm a little conservative. I think that you could, in the overall height of the building, because of the reduced size and the ductwork, you could probably save somewhere between 5 and 6 inches per floor. So for a 5-story building, they're estimating you could save as much as 6 feet. I think it's closer to 3 feet, but any savings in the physical height of a building translates into reduced construction costs. So that's another advantage of chill beam systems. They take up less physical space. And the other advantage, if it's an existing building, I've worked with a lot of architects in my career, and if it's an existing building, one of the things that they'd like to try to do is, if they're doing 100% renovation especially, is to keep the ceilings as high as possible. And so chill beams, because of the smaller ductwork distribution, you can have a shallower ceiling cavity, so you can raise the ceiling heights, and that's always a major advantage. So now we're going to talk a little bit about how you might pipe these systems up. So how are we doing for time? We're doing great. Before I get into the piping system options, Brett, do you have any questions out there?
Here's a kind of a common question. Are there filters on the chilled beams? How does that impact maintenance since it's in the space?
Yeah, so let me just, if I can show you, go back to our photograph. Our chill beams do not have filters, but you can get them with filters. And if you look at the chill beam that I've shown here, they're actually hinged. The perforated panel, let me go back to the other slide so we can kind of get a, there's actually a perforated panel on the front of the chill beam. That's right here. That's that perforated panel. So the ones that we have do not have space for a filter, but you can get them manufactured with the space for a filter, and that's where the Hepa filter would go. But these are hinged at one end. So this guy's hinged right here. And so this thing can swing down like this. When it's open, looks a little bit like this. And you can have access to the filter. Ours swing down. We don't have filters, but that allows us to vacuum out any dust that may collect. Again, remember, these coils are running dry. They don't have any moisture on them. And so they can easily be vacuumed out. And I think in the 8 years that they've been operating, we've only vacuumed them once or twice. I doubt if we've done it more than twice, to be honest with you. So that's where the filter would go. That's how it's hinged, and that's how you service them. They're very, very simple to service. And by the way, there are a variety of configurations that are available today that were not available when we did the design for Cranston, which again, we did the design almost 10 years ago. The building is 8 years old. So what we had available then was maybe a dozen or so variations, and now there are multiple variations of all kinds of configurations for chill beams. They go in the ceilings, they go on the floor, they go in the walls. There's a great number of variations. So yeah, the manufacturers have really stepped up and come up with a variety of options for people. Let's erase that. Any other questions, Brett?
No, I think we should go on to the distribution talk. That might answer a couple of these.
Okay. So here's a typical piping system that you might see out there. And Brett has an opportunity to review a lot of these proposed piping systems. And I would say, Brett, this is probably one of the more common ones that you see. Would you say so?
Yes, I would agree.
So in this case, it's called a 6-pipe system. And the reason that it's called a 6-pipe system is because we have to have chilled water above the dew point temperature. So I'll get my pen again over here. So in this case, we have a supply and return pipe supplying water above the dew point temperature. We have a supply and return pipe for low temperature dehumidification, and then we have supply and return for hot water. Now, again, depending on where you are in the country, you may or may not have the need for hot water, but we're in the Northeast and we need that. So that's a 6-pipe system. We've actually seen people have 2 hot water distribution systems, and they would have an 8-pipe system. So in each one of this is a conventional, so you use a control valve. You either have a 2-position open and closed or a modulating control valve. Over here, we have a changeover loop. So this is a 2-pipe chill beam. You can see we have a supply and return pipe. So when we're in the cooling mode, we take water from this guy over here. When in the heating mode, we take water from here. And this is a 6-way control valve. Many of you may not have seen a 6-way control valve. We actually, the folks over at Belimo manufacture 6-way control valves. I believe there are other manufacturers out there, but they were generous enough to send a couple over to our office in Cranston. So when people physically there, I have some 6-way control valves. It's actually 2 3-way valves cast into the same valve body with a single actuator, and that's what allows it to do the changeover with 1 device instead of 2 devices. And we need high temperature hot water for heating in the air handling unit or energy recovery unit, and we need chilled water. So that's where the 6 pipes come from. And if you notice, all the control is done through valves. There's a valve there, and a valve there. Okay, so that's one method. Another method is to use what is known as a single pipe system. And in a single pipe system, this is called a single pipe. You have 1 supply pipe, and then essentially that supply pipe, in this case it's 42 degrees Fahrenheit, creates a primary loop, and then we have the low flow mixing block with 2 circulators, and this would be the secondary tertiary loop. So let's get my pen again. So this down here is the primary loop. This device here, this is called a twin T, sometimes referred to as a hydraulic separator, a bridge. There's a bunch of names for it. And this is the secondary loop. This is the bridge here. There's a bridge here, and then there's a bridge right in here. So here's our secondary loop powered by this pump, and here's the third loop or tertiary loop powered by this pump. That allows us to carefully control the supply water temperature to the chill beam. Now, this is the same technology that we're using in Cranston. So we have a 4-pipe chill beam, as we've demonstrated here, 4 pipes. So we have simultaneous heating, cooling. We always have chilled water above, we always have chilled water, in this case, 42 degrees. But because of the blending or mixing capability of this guy right here, we can actually deliver the chilled water to the chill beam above the dew point temperature. And again, my supply water temperature is around 42 degrees Fahrenheit, and I'm mixing it at the low flow mixing block and delivering the water temperature at about 5 degrees above the dew point. So in my case, that's about 55 degrees. 55, ta-da, 55. Okay, so you can see instead of control valves, we're using circulators. So here's another circulator down here and another circulator here. So we're using circulators. In this case, these circulators are variable speed, just like a modulating pump. I'm sorry, modulating valves. It's like a modulating pump. This circulator right here is a variable speed. And this circulator over here, sometimes referred to as the zone circulator, and this one is the injection circulator. This one's constant speed. I'll put a C for constant and then a V over here for variable speed. So we're able to precisely control the supply water temperature that we want to our chill beam. And then we also have 42-degree water slightly above, because there's always a cascading increase in temperature. So now to our air handling unit, we can supply a more conventional temperature of around 44 degrees Fahrenheit. That gives you an idea of what's going on there. That would be this guy right here, this pipe right there. Okay, the primary air in this first example is constant flow. So we have constant flow primary air. And again, the primary air is at the right temperature, dry bulb and wet bulb, to provide latent capacity. So we go a couple of steps beyond this in Cranston. What we do in Cranston is we add a couple of other features. Instead of having a constant flow primary air, we add a variable air volume box. And by putting in a variable air volume box, we now have created variable airflow on the primary air side. So we actually modulate the primary air on a per space basis, depending on several characteristics. And we know that we can modulate the primary air from 100% airflow down to about 40% airflow. And that's how we set up our VAV boxes. We added one more device, and that was, whoops, that is a CO2 sensor. So let me go back. If you'll notice, the room temperature sensor right here is measuring both temperature and relative humidity. That allows us to calculate the dew point temperature. That allows us to set the water temperature 5 degrees above the dew point temperature. And by adding another device, we're adding a CO2 sensor. Let me erase this for a moment. Try redrawing that. We have a temperature and relative humidity sensor, and we're adding a CO2 sensor. And we can use that CO2 sensor to determine how much fresh air we need. So if we're satisfying the space dew point temperature and the space dry bulb temperature, we don't necessarily need to have more outside air. So by monitoring the CO2, we can actually reduce the amount of outside air. So this becomes a hybrid system where the primary air is variable airflow, and we have a chill beam providing the efficiency of the system. And all of these devices are controlled by a single chill beam controller right here. So that's how you can set up a piping system in order to provide very precise control on a room-by-room basis. By the way, we're providing demand ventilation on a room-by-room basis by using the CO2 sensor. And we have one VAV box and one set of circulators per zone. Now, some of it on the second floor, when we have offices that have the same physical size, the same exposure outside, the same population, we group 3 offices together. So one zone is 3 private offices. Okay, we've covered a lot of material here. And so we get to my next slide. It's one of my favorites, Brett. One of my favorites, Brett. Questions? Any questions?
You know, we have, you know, we're getting a little over 1, but past 1. Is there a rough cost construction VAV versus chill beam?
Well, as it turns out, if you remember that very first slide, so let me go back here and I'm going to go way up to the top here. That very first slide where I talked about the cooling load profile. Now let me go to this slide right here. Okay, so in the cooling load profile, let's do this one more time. Okay, so I have to kind of press the button a couple of times. Bear with me. I'm pressing the buttons, Brett, I promise. Jeez.
You're getting there.
All right, here it goes. Okay. If you'll remember, I said that the sensible heat was approximately 80%. Now, one of the things that dictates the amount of sensible heat ratio that a space experiences is the outside air. And in this case, specifically the air that's infiltrating in from the outside. So in an older building that does not have a robust envelope, the amount of air that infiltrates from the outside will drive down the sensible and drive up the latent. So what we say is the following. When the sensible load is an 80% or greater, an active chill beam system is generally less expensive than an all-air variable air volume system. When the sensible heat is between 50% and 80%, then the variable air volume system is a close tie, or it's slightly less expensive. So in other words, it's a sliding scale. As you get closer to 50% sensible heat, you need more and more ductwork capacity in order to handle the latent load. And so the more ductwork capacity, the bigger the air handling units, the bigger the ductwork. So when you start getting close to 50% sensible, or you're increasing the latent to close to 50%, then the VAV system starts to become more economical. And almost without question, whenever you have a sensible heat load of less than 50%, then chances are the ductwork has to be larger to accommodate the increased latent load. And so an all-air system is going to be less expensive. So that kind of gives you a sliding scale. Hopefully that answers.
One last question. What's the temperature? At what temperature is the water inside the energy recovery coil, roughly?
And we are currently using, let me just hold on one second here. Try to erase this. Yep. And let me just go to my little DOAS unit here. Did that work? I think it did.
Yep.
Okay, so since the reheat, the question was about the reheat, right, Brett?
Yep.
So, oh, the energy
Yeah.
recovery coil? Well, actually, the water temperature is determined by the two coils. So you have the coil that's in the supply air unit and the coil that's in the exhaust air unit. So the water temperature is, when it's running, it's somewhere around, it leaves this lower unit here. It's somewhere around, it's going in this direction. Let me make sure the direction it's going in. Get my pen out. So it's moving in this direction. So when that fluid leaves here, it's probably pretty close to 76 degrees Fahrenheit. Yeah, 76 degrees Fahrenheit. Because the air, the outside air, as it strikes this coil here, that's around 95 degrees dry bulb. And since this is coming off this coil, the fluid temperature is about 76 in this direction. And then when it's coming in this direction, it's pretty close to about 90 degrees Fahrenheit in that direction.
Perfect. Not bad. Not a bad F.
Not a bad sketch, as they say. So we get right down here to my very best favorite slide. Any other questions out there, Brett?
No, I think we covered most of them.
Great.
So you are all set.
So I would like to say thank you, everyone, for listening in to our chill beam presentation, COVID-19 Buster. It has tremendous capability to reduce the cross-contamination from one space to another. And I believe that we're going to see this technology flourish once people begin to realize not only is there an energy savings, but we also have this ability to provide an unprecedented isolation of the different spaces and the indoor air quality because of the capability of the outside air. So with that, I'm going to say thank you one more time. Stay safe. Turn it back to Brett.
Thank you, Rich. We covered a lot of ground there. And I think we need to reiterate, TACO does not manufacture chill beams. Some of the products that you've seen in the distribution of the water, we obviously manufacture, but we do not manufacture chill beams. In about a month, there will be some more, there'll be a webinar focused on how to distribute the water as effective as you can in the least cost-effective way as well. So I'll be on the alert for that. Just a friendly reminder that roughly 24 hours from today, or tomorrow, 24 hours, you'll get an email with a copy of the video and a link to your PDH certificate if you so need one. So be on the alert for that. And if some of you folks don't get it, you know how to get in touch with us. You've done that before. Other than that, thanks for your questions. Great questions today. Common. Most of them were very common, but very, very quick, good questions. And stay safe out there. And thanks, everybody. Take care. Goodbye.